Hey everyone, myself Bhavya Goyal, a student at IIT Gandhinagar. I welcome you at CodeChef and let's have a look at this question. So yeah, today's question is balanced subarrays. In this question, we are given an array A of length 3n and it is said to be balanced if it contains exactly n occurrences of 1, 2 and 3. So for example, this array 1, 2, 1, 3, 3, 2 is of size 2 times 3, which is 6, and it contains exactly two ones, two twos, and two threes. Hence, it's a balanced array. 3 2 1 is also a balanced array because it contains exactly 1 1, 1 2, and 1 3. Now, 1 1 1, 1 2 1 2 1 2, and these are not balanced arrays because they do not contain exactly an occurrences of each of 1, 2, and 3. Now we're given an integer k and we need to construct any array A of length at most 10 is to the power 4 consisting of only the integers 1, 2 and 3 such that it contains exactly k contiguous subarrays that are balanced. So we need to create or print another array A such that it contains exactly k number of contiguous subarrays that are balanced. And a subarray is obviously like a pair of integers L comma R such that A of L plus 1 dot 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 A of R is balanced. Now it can be proved that a valid array always exists and we just need to construct an array without thinking about minimizing the length of it. So any array that is of length less than or equal to 10 raised to the power 4 is a valid array. In the constraints we're given the number of test cases to be in between 1 and 50 and the value of k in between 1 and 10 raised to the power 7. Now let's look at sample input once to understand it better. So in the first test input we have k equal to 1. So we need to create an array such that it has exactly one balanced array or subarray. So 3, 1, 2, 3. This is a balanced subarray and it has exactly one balanced subarray, that is this 1, 2, 3. Now let us see for k equal to 2. We have 1, 1, 2, 3, 1. It has exactly two subarrays that are balanced, right? So these are the two subarrays that are balanced, and we can see that there does not exist any other subarray which is also a balanced subarray. So yeah, that's it. Now let us look at the solution. So let us start putting 1, 2, 3, 1, 2, 3, 1, 2, 3 consecutively because we know like we can easily see the pattern that it's gonna give us the maximum number of subarrays that we can get, right? So if we have 1, 2, 3, then there would be n minus 2 subarrays of balanced subarrays like this 1, 2, 3, then this, then this, then this, and this, and so on, right? So there would be exactly n minus 2 subarrays if our n is some 3 times I, some multiple of 3. So for example, over here we have 15 inputs and I is equal to 5. So there would be exactly 13 arrays which are balanced, 13 subarrays which are balanced of this form 1, 2, 3, then this, 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 and so on, right? And there would be exactly n minus 5 subarrays which are balanced of these six values, right? There would be 1, then 2, then 3, then 4, 5, and so on up till n minus 5 such subarrays, right? And similarly, there would be n minus 8 subarrays of this length, 1, then this one, and so on, right? And similarly, there would be n minus 11 of this length, 1, 2, 3, and this one fourth, right? And then there would be n minus 14 subarrays of this length, which is 1 only, right, in our case. So these would be the total number of balanced subarrays we'll be having if we keep on putting 1, 2, 3, 1, 2, 3, 1, 2, 3 consecutively, I number of times, right? Now, if we sum them up, then how many total balanced subarrays do we have? So this is balanced. So it would be n minus 2 plus n minus 5 plus n minus n dot dot dot. Or if we write it in terms of 3 times 3i minus 2, like if we replace n with 3i for some integral of I, then it will be 3i minus 2 plus 3i minus 5 plus 3i minus 8 and dot 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 up till the last element would be 1 if I is an integer, right? And we can easily solve it using AP. So we can see that it's forming an arithmetic progression 3i minus 2, 3i minus 5, where the first term is 3i minus 2 and the common difference is minus 3. So this would be the total number of subarrays that we have, right? And now we're given that n will be as big as 10 raised to the power 4. So we'll try to figure out that what is the maximum value of subarrays, balanced subarrays that we can have, the maximum number of them, right? So if we, let's say, keep placing 1, 2, 3, 1, 2, 3, and so on, then what are the maximum number of subarrays that we can get? So for n equal to 10 is to the 4, or we can put I equal to n by 3, the summation n minus 2, n minus 5 dot 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 would be almost equivalent to this. And what was our maximum value of k? 10 is to the 7th. So we have 1.6 into 10 is to the 7, that is greater than 10 is to the 7, right? So it should always be possible for any value of k to create a possible array A which have exactly k number of balanced subarrays, right? Because n can be as big as 10 to the 4. Now let's think of a greedy approach, right? So if we call this value as, let's say, some s, then do you think it's always better to take as big s as possible? Like put as many 1, 2, 3s consecutively as possible. Subtract the number of subarrays that we got. So if this is s, just do k minus s, and then start creating some more subarrays like this. Like, should that work? So the approach, the greedy approach is keep taking the largest value of this I by 2 into 3i minus 1 that we can take. Now let's consider a potential issue with that. So let's say k is equal to 2. The largest value of the sum that we can put is going to be 1 only. So we place just 1, 2, 3. And now our k becomes 1 because we got 1. So k was 2. We placed 1, 2, 3. So we got 1 balance subarray. So we subtracted it by 1. Now k is 1 and put 1, 2, 3 again. But this has more than two balance subarrays, right? One is this, one is this, one is this, one is this. So there are so many balance subarrays, right? So how do we fix it? So it turns out that like one possible turnaround for that is we place two twos in between. So let's say our k was equal to 6. We'll take the largest sum possible. So for I equal to 2, we can have 5 number of subarrays. If we place I equal to 2 here, that is 2 by 2 into 6 minus 1. So it turns out to be 5. So we can create 5 subarrays with I equal to 2. So these are the 5 subarrays. And then we can place a single subarray over here. And if there are twos in between, then this part and this part would not have any overlapping balance subarrays, right? So in total, we'll have 5 subarrays, balance subarrays from here and one from here. And in total, we'll be having 6 balance subarrays, right? And this is pretty much the whole solution as well. It was a constructive problem, so I guess this part was the most crucial one where we just need to, like greedily first of all think and just print it up. Now, one last step is as an exercise for you, that is to prove that if we are placing the numbers like this in this greedy manner, then we'll always be able to create an array A of size less than or equal to n, that is 10 raised to the power 4, for some k equal to 10 to the power 7. And you can see this proof in the written editorial for your reference. But yeah, I'm not going to explain that. That's an exercise for you. Now let us see the solution in Python. So we'll begin by taking in the input of test cases. We'll take in the input of k. We'll initialize our answer as an empty list. We'll run I from 10 to the power 4 to 1. That is from like the largest value of I that we can take to the smallest value. We'll run a while loop, that while we can take this summation, while this summation is less than or equal to k, just keep appending I number of times that array, that like while this is true, just keep appending 1, 2, 3, 1, 2, 3, 1, 2, 3 I number of times. So over here, what we are doing is we are just running a loop from 0 to 3 times I and printing j modulo 3 plus 1. So it will print 1, 2, 3, then 1, 2, 3, then 1, 2, 3. So it will just keep printing that in cyclic order. Once we are done appending that, we'll append two twos to encounter for the non-overlapping case. and then we'll subtract this summation of our AP from our K. In the end, we'll print the length of our answer and we'll print our answer as well. So this is pretty much the whole solution in Python. Now let us see the solution in C++. So we'll begin by taking in the input of the number of test cases. We'll take in the input of K. We'll define our answer vector. We'll run a loop from the largest possible value of I to 1. Now while this summation of AP is less than or equal to K, keep appending I number of 1, 2, 3 subarrays. So we'll append the subarray 1, 2, 3, 1, 2, 3, 1, 2, 3 I number of times. We'll subtract this AP summation from the K. We'll append back 2 inside our answer to consider for the non-overlapping cases. And in the end, we'll print the size of our answer and we'll also print our answer vector. And yeah, this is pretty much the whole solution. I hope you liked it. Thanks. Bye.